Okay. So, we are looking at this resolution method, and we had said that we came to the resolution method because of the fact that forward chaining and backward chaining were not complete essentially. Okay. Now, the resolution rule, if you keep applying repeatedly, is not complete in general. To give you a simple example, so what is the notion of completeness? That if something is entailed, then it must be derivable essentially. So, to give you an example, if you have some random database in which there is only one statement P, it could be first order logic, it could be propositional logic, it does not matter, and this entails the statement S or not S, which is not surprising, because S or not S is a tautology in any language. So, it must be true, and in fact, you do not even need that P to be true essentially. But as you can see that there is no way of deriving S or not S from P. So, in a sense that you cannot derive not S, or in other words, from this statement P you cannot derive this S or not S. So, in that sense it is not complete, but resolution refutation is complete. And so, what do we mean by this? That if the input is unsatisfiable, then one can the empty clause. Which in our language we can say that if a set of formulas S entails the empty clause, which means it is unsatisfiable. Empty clause stands for false essentially, and if you can derive false, that means your original set must be unsatisfiable or a contradiction. So, if this, then you can derive, and this was shown by Robinson when he actually proposed the resolution method, that the refutation is unsatisfiable, that if you want to show that something is, the refutation is complete, that if you want to show that a set of formulas is unsatisfiable, then there will always exist a proof that you can find essentially. So, you can derive the null clause. Now, of course, this does not create any particular difficulty for us, because in general if a set of clauses S entails a formula alpha, and which is what you want to show, that alpha is a consequence of the set of formulas S, then if you take the union of S and negation of this alpha, then this is unsatisfiable. So, remember that entailment basically stands for basically a tautology of some kind, that S implies alpha is true. So, a simple way to make it unsatisfiable is to take the negation of what you want to show, which is of course, we know it as proof by contradiction, added to the set of clauses, and then entailment follows, that the empty clause is this thing. And because we have said that this is true, this is a definition of completeness. We have already spoken about soundness. So, in fact, you can replace this if then statement with an if and only if statement, that you can derive the null clause if and only if the original set is a contradiction essentially. So, it is not a problem to work with refutation method essentially. You can easily adapt that to this thing essentially. So, we are talking of FOL in general, and so with resolution refutation so we have already seen that the choice of your proof method determines whether it is complete or not, but so with resolution refutation it is sound and complete. There is also a third property that we are interested in, is that will our algorithms terminate essentially, that is called decidability, and it turns out that for all kinds of methods FOL is it is only semi decidable. What do we mean by this? That if the input is unsatisfiable, we can derive the null clause. So, for example, one could use something like breadth first search. But if the input is satisfiable, could loop forever. So, let me give you an example of that, and we have seen also in backward chaining, for example, that you could write rules which could go into infinite loops essentially. So, just look at this rule. This says that if so, let me first write it in logic. That if the successor of S, remember S is the successor function, if the successor of S is less than y, then x is less than y, and we can accept that this as a true statement. So, which if we write in clause form, we will write it as less than So, let me use question mark here. So, I convert P implies Q into not P or Q and write it as a clause essentially. Now, supposing that our goal is that is 0 less than 0. So, first of all, so when we say that is a goal, the basic question we are asking is that is this entailed by the knowledge base, and our knowledge base has only one sentence, and you can see that this will not entail. So, anyway, so we negate it. This is our strategy for refutation, and add the negation of that clause, which is not you can see that if I resolve these two clauses, I will cancel this not less 0 0 with less than x y by saying x equal to 0 and y is equal to 0, and I will get a new clause successor of 0, which I will write as 1, or let us just write it as successor of 0 to avoid confusion. Now, we can again match this with the same clause. We have only two clauses to start with, and we can produce a new formula. And this process can continue. Indefinitely. So, you can see that with this just these two statements, we can get into an infinite loop. We can keep resolving this whole process to keep generating new clauses, which can be resolved with the first clause again and again essentially. So, this goes into a loop. Okay. But there are still some nice things we can do, and we see that. So, it's semi decidable in the sense that if what you are trying to show is indeed a consequence of your knowledge base, then you will terminate in a finite amount of steps. And then we have also mentioned that we can, for existential queries, we can do something like answer extraction. So, we had seen for example, that if you know that all men are mortal, if you ask a query, is there someone who is mortal, then you could have come up with an answer that yes, depending on what your database has, whoever is listed as a man, you can infer is mortal essentially. So, some people have suggested that we can use an answer predicate to explicitly extract an answer. So, let me take the example of the plus thing that we had developed earlier. So, remember that the clauses for addition, one of them that was that if x plus y gives you z, then the successor of x added to y gives you the successor of z, and this is something that we had seen. Of course, we also had a base clause, we will see that in a moment. Now, supposing our goal is to ask whether this formula is true, 2, 3 or, and if you we just follow the procedure, we negate it and add its negation here, which is negation of plus 2, 3 or, and we add a clause which we call as answer, and we put in the variable that we are interested in there essentially. So, this is the answer predicate, and we of course need to modify our termination criteria. Is that if earlier we used to terminate when we derive the null clause, now we will terminate if our clause contains only the answer predicate essentially. So, we can go through our process again. So, we can resolve this with this. And what do we get? Naught plus. So, this time I will just use natural numbers 3 R 1 or remember that the unifier for this will have R is equal to successor of R 1, and of course, x is equal to 2 and y is equal to 3. Sorry, x is equal to 1 and y is equal to 3 essentially. From this and again from this we will get naught plus 0, 3 R 2 or successor of R 2. Now, this will resolve with the second statement in our knowledge base, which said that plus 0 with z. Okay, so, we will not get the null clause this time, but what we will get is only this answer successor. I will just write 3 here, and you can see that we will now terminate with this. So, at termination the answer predicate tells you what is the answer. What was the question we asked? We asked what is 2 plus 3, and this answer predicate says that the answer is 5 essentially. So, the successor of 3 is 5 essentially. Remember the example that we had we had considered in which our K B was the following. On table A, on table B, green A or green B. So, we have these 4 clauses, and if our query is does there exist something which is on the table and green, and we had shown that resolution method will allow you to do this. Now, what will we do? We will convert this into clauses. So, on table we will negate it and convert it into clause form. So, what will we get now? So, what are the clauses? This is one clause, then on table A is another clause, on table B is a third clause, and green A or is the fourth clause. And we had shown this, that from these 4 set of clauses, this is the negation of the goal that we have, we can derive the null clause. What do you expect we will terminate with? What will be the answer to this question? So, what is the question? The question is A is on the table, B is on the table, and at least one of them is green, and then we are asking, is there something on the table which is green? The answer is yes, that we have shown already that we can derive the null clause, but now we have added the answer predicate to this. What will that contain? I will leave this as an exercise for you, but you should verify that at termination you will have the following. That if you did the same resolution steps and carried forward the answer predicate, you will get the answer that obviously you can see that from the knowledge base you cannot say whether A is the answer or B is the answer, because one of them is the answer, and in fact the resolution method will come up with this if you are using answer predicate, that either A is the answer or B is the answer. Sometimes you have to be a little careful here. So, let me take yet another example. Let us say that we are analyzing some detective story or something like that, and what is given to us is the following set of clauses. I will just write the clauses and I will ask you to reinterpret them as first order logic statements. So, I will use the predicate A, predicate C to stand for culprit, because I want to keep writing it over and over again. I do not want to spend too much time writing that. So, this is given to us. So, without using real names, we will use the names A and B. So, this statement says that either A is a culprit or B is a culprit, that is known to us, that is given to us, essentially. You could have written this statement as follows. For all x You could have written this as well essentially, and basically the two are equivalent essentially. And we have seen that one of the problems in first order logic is how to express things essentially. So, this is one question that one should look at essentially. And then we have some more clauses. There is a clause which says that I will just use uppercase in Prolog style to stand for a variable here. So, when if you read this in first order logic, you should really read it as saying that culprits wear red shirts essentially, or for all x, if x is a culprit, then the color of x's shirt is red. So, remember we had talked about properties and there are different ways of writing color and so on. So, I have chosen this particular set of predicate as an exercise. You should convert to triple. But I will leave that as an exercise for you. There are different ways of expressing the same fact. So, anyway, so we are told that culprits wear a red shirt, and then we are also told that one of the two culprits that we have, A, he was actually wearing a blue shirt. And then we have some general knowledge about colors, that colors are different, which we can express as follows. So, if you go and sort of look at this a little bit carefully, essentially what I am saying that color C1, either color C1 is equal to color C2 or they are different essentially. Both you cannot have u v some person u for some object v, let us say shirt, if v is a shirt, wearing a blue shirt and a red shirt at the same time, one of them must be at least false essentially. So, this is basically saying that colors are distinct essentially, and then I have in my knowledge base certain statements like red is not equal to green and blue is not equal to red and all kinds of such statements. So, I just need blue is not equal to red. So, I am not writing the others here essentially. And so, this is a knowledge base given to us. This is one clause, this is another clause, this is a third clause which says that A was wearing a blue color. This is a clause which says colors are different, that you cannot wear the color of your whatever you are wearing is unique, and this is a clause which says that red is not equal to green and blue is not equal to green. Now, we are given this query that there is a culprit. Okay. Which again we negate and replace it by not C. So, let me use a different variable name x1 here or answer x1. I am using the answer predicate here essentially. So, one thing that you can observe about the resolution method is that basically it is a method which shows that something is unsatisfiable essentially. So, I have got this set of clauses. I have said that either A or B is a culprit, culprit is wearing the red shirt, A is wearing the blue shirt, and I am asking who is the culprit or is there a culprit essentially. Obviously, there is a culprit because we have said that culprit A or B is a culprit essentially. Now, one thing is that you can actually make a derivation which works as follows, that you derive from this something. What do you derive from this? So, let us say you put x 1 equal to A. So, you will get C B or answer A, and then you can from this and this you can derive answer A or answer B. Of course, this is not telling us anything. We started off by saying that A is a culprit or B is a culprit, and then now this is telling us that A is the answer or B is the answer. But in this particular example, as you can see, we have more information, we can in fact identify the culprit. So, what I am trying to highlight here is the fact that the resolution method may terminate like this green derivation by saying that yes, there is a culprit indeed, but without identifying who the culprit is and simply stating that either A is the answer or B is the answer, but we can have a derivation essentially. So, for example, if I use this fact, then I can get not color U V. So, C 1 is blue here or not color U V red. Okay. Then I can take this one and I can take this one, and by saying that U is equal to A and V is equal to shirt, I will get not color A shirt red, because I said that the A shirt is blue and this one says that it must be either red or blue. So, I get the clause that A shirt is red, and from that and this I will get not culprit A. Okay, so, we know that A is not wearing a red shirt, and from this and the fact that culprits wear red shirt, we can infer that A is not the culprit here. Then we can resolve the fact that there is a culprit with this one to give us the fact that C is the culprit. In fact, by now we have arrived at the answer, but since we are looking at the resolution refutation method, you can see that between this clause and the goal clause, we will terminate with answer B. So, as we saw that there were two derivations, one which is in green did not pinpoint the culprit for us, but we have an alternate derivation which can exploit the information that we have in the knowledge base that culprits wear red shirts, and since we know that A is not wearing a red shirt, we could figure out that A is not the culprit and that B is the culprit, and in fact, that shows up in the answer itself essentially. So, if the resolution method had taken this as a derivation, then the answer would have been answer B. Notice that both answers are logically correct. If you say A is a B is a culprit, it is correct. If you say A is a culprit or B is a culprit, even that is correct. So, there is nothing wrong which is going on, it is just that we have not been able to identify what is the thing. Okay. So, in the next class we will take a closer look at equality, and we will see that equality is a special predicate. It is not just like any other predicate like father, mother, loves and so on, because it carries with it a certain amount of mathematical knowledge, which we will need to make it explicit if we are to exploit the fact that equality has certain properties. So, we will do that in the next class.